So, welcome to class 4 of stochastic control optimization. So, today we'll be talking on problems of sequential decision making. So, yesterday we saw an example. I'll just quickly recap the example that we saw yesterday. It was just a simple two, two, two-state scalar problem where you had uh, x1 equal to u0 plus w0 and x2 equal to x1 plus u1. And this W0 was your noise in the system, and it had some distribution, and the distribution was -1, 1, with probability half in both the cases. And your U0 and U1 were your control variables. You could control them. And X1 and X2 were state. You were asked to minimize the expected absolute value of X2. So you have to make a choice of decisions. We saw two cases where you were asked to make the choice of U0 and U1 upfront without any knowledge of what was happening. That was the first case. In the first case, we saw that the optimal value of x2 was 1. Right? You could make x2 as low as 1. In the second assumption, it was that first you take decision U0, then you observe what x1 is, and then you take decision U1. In that case, the same optimization problem, the output you could go down as you can go down to 0. So you see, uh, when you take when you have this information coming in sequentially rather than taking it all at upfront in the beginning of the thing, you'll be able to better optimize because you have now more information about the randomness in the system. Okay, so uh, yeah. so this is what we saw yesterday. This example we saw yesterday. Now, problems on sequential decision making is actually it tells something about the way which we are given the information about the system. That makes a difference in the way we take the decision and also how well we can perform. Right. And so today what we'll see is we'll see how do you generally define the sequential decision making. And this is now entering into that MDP type of formulation. I'll not directly go to MDP formulation, but I'll try to bring up the intuition on why MDP type of formulation comes here. So we'll define problems mathematically, and then we'll come up with how do you take actions or decision at multiple stages. And your goal would be to minimize cost, right? So first I'll give the mathematical background on sequential decision making. So there is one model known as the state space model. For sequential decision making. So this okay, in most of the community, most of the okay, in control community, they call this as stochastic control. Uh, in the control community, and in computer science and I think operations research, they call this as MDP, right? In operations research and computer science. So both have similar things, slight variation in both the things, but it's basically the same thing. You're trying to do sequential decision making. So how do you mathematically define it, right? So basically, the first assumption that we have here is that the time evolves in discrete steps. So when time evolves in discrete steps, anything that happens between two time steps is not completely observable, or it's not completely known to you. You only see at these discrete time instances what happens to the system. Like you can observe what happens to the system at discrete time steps, right? So basically, time is discrete. And what this means is t that I'll denote with k belongs to some 0, 1 to n minus 1. And n is usually less than infinity. For now, we'll take n less than infinity so that we have finite horizon. And you can either observe or take an action at these discrete time intervals. You can't do anything in between those time intervals. Okay? But the system evolves in between those time instances, but you'll be able to just take actions or observe the state of a system at those discrete time instances. It doesn't mean that the systems are discrete. You're just modeling the system in a discrete way. Okay, so
So I have a query here that at the discrete timestamps, so do we have a central control, or the entire control is distributed
oh,
in
so
in the
yeah,
first case?
yeah. So yeah, your doubt is single control or distributed control. So right now I'll be talking just on single control. I'm not talking anything about distributed control. So uh, uh, for the first initial stage, MDP formation of MDP, we'll just talk on single control. So single control in the sense you could have a control vector, like you could have U1, U2, U3, a control vector. Mm, but that's it. It's not distributed. Like it's just a single control. Today we'll talk about an example also. In that, I think it will be more clear. Uh, but you can talk about distributed control. It's not that you can't talk about it, but you can. But we'll just do the single control. So you have xk, which is your state of the system at time k. Okay, and so intuitively what state means is state is some real number or a vector or some variable which if you know xk then you're able to describe the complete configuration of the system. So it's basically it tells you everything you need to know about the system. Xk is that is a state of a system. That is what we call a state of a system. Uk we call as control action or decision that you choose at time k. And wk is your random parameter or a disturbance in the system or whatever. It varies as you model your system. So but basically wk is the randomness in the system which you don't know but you know some statistics about it. That's it. N is your time horizon. And for now, we'll keep time horizon finite. You could have problems where your time horizon is infinite. But for the first initial classes, we'll have time horizon to be finite. So when we take an action uk at time k, the state evolves from xk to xk plus 1, right? So what happens is you have xk, and then you take an action uk, and then your state evolves to xk plus 1. And then you observe xk, and then you take action uk plus 1, it evolves to xk plus 2. This is what happens. But in the middle, what happens is once you know xk, you take uk, and then there is some noise wk which goes into the system, and you're depending on xk, uk, and wk, you get your xk plus 1. Similarly, once you have xk plus 1, you take the action uk plus 1. After that, the system gives some disturbance wk plus 1, and based on these three, it evolves to xk plus 2. So basically, what happens is your xk plus 1, the future state, is some function of xk comma uk comma wk. And this wk is the randomness in the system. uk is your control variable and xk is your state. Since you have randomness here, what xk plus 1 you will see would also be random. And this fk is known as the dynamics of the system. Now, this could be known in some models. This dynamics could be unknown. Okay, so if you don't know the dynamics, then basically it goes into learning part. So you don't know what dynamics are. You don't know the physical laws of what your system governs. So what you do is you sample, you just choose some actions and then sample, just get outputs from the uh, system and then try to find this function. That is all the learning theory. The neural networks, the learning theory is all just trying to find out what the dynamics of the system are, right? But in stochastic control, it's you know something about the dynamics. Either you know the dynamics or you know some statistics of the dynamics. If you know them, then what decision you will take is what is stochastic control. I hope the uh, relation is clear, like uh, what learning is and what uh, stochastic control is. Stochastic control is you either know the dynamics or you have some estimate of what dynamics are. Yeah. But if you completely don't know what dynamics are, then you basically do learning is by you take actions, sample, look at how the state evolves, and then based on your sample paths, you come up with some uh, closed form black box which gives you the dynamics. Yeah, you had it out. Yeah,
So how to define this FK, or how this FK is taking place?
yeah. That is a good question. So FK is basically if you know your problem, then that problem would have some mathematical model which governs the problem, right? So FK is basically, so you could take any mechanical system and say that, okay, your force, acceleration, your distance, speed, velocity, acceleration are your states, and you know how force and how force affects the speed and acceleration and all, and you have a nice closed form solution of how your unicycle model or some mechanical model works. If it is an electrical system, then you know current, voltage are your states, and given the circuit or whatever is your electrical components, you can come up with the relation between current and voltage in all the parts, and you would have the dynamics, right? Similarly, today I'll give an example of inventory control. There you'll understand what the dynamics actually are. But sometimes, okay, that is one part, and then you'll go into, okay, I don't know dynamics, I don't know FK, but then can I see some statistics on how the states evolve, like some probability distribution? Could I give say that, okay, if it is in state XK and I take action UK, then with some probability it will go to state one, with some other probability it will go to state two. If even if I can model my systems in a Markov decision process, then that is also that will also come under your your dynamics. So yeah, does it answer the question?
So is this a transition function kind of a thing, wherein from a state, what will be the next state of the system is governed by
Yes,
this FK?
yes. Yeah.
Okay.
So first we'll look at problems where you know the dynamics, where you're pakka sure the dynamics, you know everything because I tell you everything of the problem. I tell you the problem part by part. Then second, we'll look at problems where uh, you don't know the dynamics, but you know some set, like okay, with some probability something will happen, with some probability something will happen. You know the probabilities. Then also it's like then also that probability test matrix is also known as a dynamic system. We'll get to it. We'll get to it. Okay. So this is your dynamics, and then your goal is to basically minimize the total cost. Right. So how does the cost function look? So cost function looks something like this: minimize expectation of gn xn plus summation k equal to 0 to n minus 1 gk xk comma uk comma wk. Okay, so first I'll tell you what this xn is. This xn is the terminal state. So yeah, when I say your time horizon is n, I mean that you go from 0 to n minus 1. Suppose you're at xn minus 1. you take the decision un minus 1. Your system gives you a random variable wn minus 1, and then you get xn. That's it. You can't take any other decision. So your decisions basically go from u0 to un minus 1. And once you reach xn, that is your terminal state. Your system stops there. You don't do anything else further. Right. There are problems where you can model this as infinite horizon, where the system doesn't stop at all. It keeps on going, keeps on going, keeps on going. But for now, we'll assume that there are finite steps in the system. Like you're looking at just finite steps, and it stops at xn. So once you stop at xn, you're always at xn. You can look at it like that. Like you stop at xn, you're always at xn. And being at xn incurs some penalty or some cost being in that state. So this is the cost. This is the terminal cost. And these are known as your stepwise cost. Or yeah, stepwise cost. I forgot the time, but it's fine. These okay. So now, why am I taking the expectation here is there is only randomness in one place. This wk is random, but then uh, each of the xk depends on your wk. So your next xks would also be random because you'll have a whole sample path or whole trajectory of um, states which are random because you have this random noise in the system. And hence your xn also would be random. So if you replace all the x with a function of this and you do a recursion formula here, you will just get randomness throughout in all the states and in all the way. But yeah, I think for now this is fine. In later classes, we'll see how to solve this problem. This more general, this more a general setting saying that okay, you'll have some cost function gn, you'll have some stepwise cost function gk, you'll have some um, yeah. And what you need to decide is you need to decide these u zeros to u1. Yeah, these are known as stage-wise costs, not step-wise costs, sorry, stage-wise costs. Okay, so now here the assumptions of your information gathering comes into play. There are two types of problems that you can formulate from here. One is an open loop problem. So one is an open loop problem where you choose the whole vector u0 to u1 without any knowledge about the system. When I say without any knowledge of the system, I mean that you don't know what x zeros or x ones are. You just you are just given this problem, and you know this. That's it. And uh, I ask you what is the vector u? U vector means that u0 to un. Sorry, this un minus 1. Un minus 1, those vectors, just tell me those vectors, right? The second is the closed loop problem. The closed loop problem, uh, you first tell me what u0 is, then you give me u0, then I run it in the system, I get x1, I tell you what x1 is. And then based on x1, you say, oh, okay, take u1 as this, and then you give me u1. And then I run it through the system, I get x2, I tell you x2. You observe x2, and then you say, okay. So the closed loop problem is basically a sequential decision making where you depend on history, right? So basically, UK depends on your history. Now, what all you observe is you observe xk, but you also know uk minus 1, you also know xk minus 1, and so on, and you know x0 and u0. So you know the whole history, and based on that history, you take a decision uk. Okay, here the important point to know is you don't know wk. If you know wk, then there is nothing to the problem. You don't know wk. Okay. Now, one subclass of this problem is I can take uk to be a function of just the previous state xk. Right. This is a special class of problems that we will be very interested. We'll be looking at these type of problems. These will be somewhat similar to the MDP problems that we're talking, right? A harder class or would be looking at the whole history and then taking the decision. But then you could just ignore all this and just look at xk. So it's a subclass. The subclass is just look at xk and take the decision. So uk equal to f of xk. This looks like the feedback problem in a closed loop. So hence it's known as a closed loop problem. Okay. Well, okay. Yeah. The most important point is UK is chosen with knowledge of XK. You know XK, but not WK. Okay, so I'll just do very quick recap. This was your sequential relation model. Uh, this is basically your MDP. I'm basically introducing a very raw form of MDP. You have your state space, you have your action space. Transition probabilities I have not yet defined, but this would become your transition probabilities. And this randomness would play a role in that. Yeah, and you have time horizon in that. Yeah, so you have a cost function for the terminal state. For each and every stage, you have a cost function. Your ultimate goal is to minimize this cost function. So how do you choose U0 to U1? Okay, so first I'll give an example of a problem. It's the inventory control problem. And what we'll see is uh, once we see the example today, basically what we'll see is we'll not go in solving any problems. Today, I just want to give you an intuition that making decisions on U0 to U1 is basically too difficult. Like you can't say anything on, you can't give U0 to U1 exactly. What you can do is you can give some strategy saying that, okay, if x p plus, if some xk or xi is in this state, then do this. If xi is in this state, then do this. You can make out plans like this. So you can't give directly, okay, if you can't just say directly, okay, take this action, take this action, take this action, take this action. You can give out some plans. And those plans we'll call as strategies or policies. Right. So from there you'll see that you have these policies, and then we'll go into what are the different types of policies you can come up for these. And once you have all those, then we'll define MDPs and solutions to MDPs as policies. And then we'll answer the question of what is the optimal policy that you can get given an um, problem that is modeled as an MDP. Okay, I hope the structure is clear. How the classes, how I'll go through everything. So for today, I'll just give the intuition that this problem is not well posed. That will be clear from the example. So what needs to be done is some modification needs to be done to the problem, and what modifications need to be done, that will be talking today in today's class. That's it. Okay, so in first I'll explain what inventory control is. You have a shop, you're selling some things. Now the question is how much inventory should you be ordering at each day? Okay. Inventory gets consumed each and every day. So some people come and buy something from your shop, but how many people come is random. That you don't know, right? But the demand arrives, they buy from you, they take away some. You have something left in your inventory, but then the next day you have the question: okay, do I want to buy more? If yes, how much is the question? So yeah, you have XK stock available at the beginning of kth period. So, okay, when I say this, I'll just give an intuition of what is happening here. 0, 1, 2, so on, somewhere middle k, and then n minus 1 and n. So when I say that the stock is available at the beginning of the kth period, I mean at the start of the kth period. At exactly that time instant, you know what the stock is, right? Okay. And UK is stock we will order in the beginning, of kth period. Okay, one assumption that I'm making here is that delivery is instantaneous. It's a very bad analogy from the modern world, but delivery is instantaneous. So you order at the same time instant and you get that stuff. You order here, you know X0 here, you order here, and you get the delivery immediately. And here you have U1, and here you have U2. So one way of thinking this is that delivery time is very much negligible to the decision epoch. So this whole thing is your decision epoch. And in this whole thing, your system has trajectories like people come, people go, people buy stuff. But you're not keeping a look at the inventory saying that, okay, do I have how much inventory I have left? You sell stuff the whole day, random, how many stuff has been sold. Then at either at the starting of the next day or that evening, you get the state X1, you order, the next day morning, you get U1. Okay, maybe we can model it like that. Yeah. So you get X2 and then the system evolves in this middle period. Okay. And WK is your um, demand, but this is not at the beginning of kth period. This is during time period K. Okay, why am I stressing on beginning and during time period is because this will uh, help you understand when decisions are happening and when I'm observing my states and when am I transitioning when I'm transitioning from state to state, there is something happening in the system which I don't know, but it goes on through a huge amount of time in the decision. So basically, I'll write out the sequence once again. The sequence is xk is known, then you choose uk, and then wk is realized in the real world. Okay, so uh, yeah, okay. One more assumption I'll make is that inventory can become negative. That is one more assumption I'll just throw out. So when inventory becomes negative, so basically x2 can become negative. When it becomes negative in the sense that uh, suppose you had 10 units in your inventory, but then you got a demand of 20. So basically you're at minus 10. So that minus 10 you can do it in the next time slot, but your state goes to negative. So if your state goes to negative, that means that your backlog, your demand is backlog. So you have not able to fulfill the demand, and hence it has gone to backlog. So could you tell me what the dynamics of the system would be? Like what would be xk plus 1 in terms of xk, uk, wk? So mm, mm, okay. So xk plus 1 would be xk, the previous time how much amount you had, plus UK. Now you have ordered UK amount of stock minus WK. WK people have come and taken away that much amount of stock. Usually there would be a plus sign, but by this plus sign I mean max of xk plus UK minus WK comma 0. So it can't be negative usually, but then I put the assumption that your states can be negative and hence you remove this. And hence you have a very nice linear dynamics. Otherwise, it's basically not. Usually, it's non-linear. Okay. So I hope this is clear. So this is your dynamics. This is how your state evolves each and every time. There is randomness in the state. It's not you don't know everything about the system. There's randomness from this WK. Okay. Cost function. So you have R of xk, which is basically if xk is negative, then basically you have a penalty per shortage because you are not able to serve customers. If xk is positive, then also you pay penalty because you have storage costs. Second is your action. So because you purchase UK amount of stock, so this is your purchasing cost, and C is equal to your per unit cost. And you have this terminal cost of RXN, which is your terminal cost, which you can think of it as your you're left with XN amount of inventory. Yeah. So you have to store them or something. So some terminal cost. Okay, so my cost. So now my objective is to minimize expectation of RXN terminal cost plus summation of k equal to 0 to n minus 1 RXK. This is your um, this state cost, your either storage or your shortage plus CUK, your purchase cost. Okay. So now if you look at here, so your problem is you need to find these U0 to U1 and your UK is greater than or equal to 0. This one constraint, that assumption that takes that you can only order something, you can't return back something. So at every instant, you have to take a decision whether you want to order something or not. Right. Now, when I say this problem is ill-posed, I mean that, okay, I'll give you two scenarios. One is action scenario and one is strategy scenario. So while you're taking action, you have f of xk and then you can take uk. But then xk is random because you don't know where xk would be, right? You take u0, you'll get something, and then you have this randomness in the problem. So instead of exactly choosing the action, what you choose is you choose a strategy or you choose a plan. What the plan tells is, if I have some amount of inventory, say suppose my xk is 50, then you would say, okay, then uk is I'll order 20. Okay, no, but if I say xk is 100, then okay, take uk to be 10. If xk is 150, then you say uk is 5. If I say xk is 200, then you say uk is 0. You should have this sort of a plan saying wherever my xk could take because of the randomness of the system, I always have an action that I can associate with that state, right? So now basically what this whole thing is just a functional mapping between xk and uk. So basically you're choosing mu k, a function which takes an output and gives you, which takes a state and gives you a control action. And now you're trying to find this mu k function. This mu k function is known as a strategy. So is that clear? So um, now I'll try to minimize the same thing. But now instead of minimizing over u zeros, I'll be minimizing over mu ones. So this is a sequence of strategies, or you can call them as mm, now you're searching in the space of functions. You're not searching in the space of vectors anymore, right? And now why do we need to go from this vector to a functional dimension is because of the randomness that you have. So because of the randomness, you can end up in any state with at least some probability. And depending on that, you have to make your action that, okay, if I end up at this state, then I'll take this action. If I end up at this state, then I'll take this action. That function tells you that. So you need to come up with functions here, right? So it's like you have a plan for every time step. And the strategy here need not be the same for every time step. It could be different. Like mu0 could be that, okay, if I end up at 150, I'll buy 100. But your mu 10 or 20 could be that, okay, if I end up at 150, I'll buy only 5. Because I know that at mu 10, I won't get that much high demand or something like that. So basically, what you have is you have your actions, which are real numbers or vectors, but your strategies are functions. And you had to go from real numbers searching in the space of real numbers and vectors to the searching in the space of functions because of the randomness in the system. If there was no randomness in the system, then you would exactly know what your xk's are. You take zero, you use zero, you exactly know what your x1 would be. Since you know what your x1 would be, then you can it is an optimization problem, just an optimization problem that you need to solve. But since you have randomness here, it's not just an optimization problem, you need to come up with something else. Okay, so I'll just give, okay, for today, I'll give an example of how a policy looks. Yeah. So one example of a policy would be, so basically your policy mu k is you have state space to your action space. Your state space are basically the set of all the, so here in this problem, your state space is your R because xk could take any real number and your A is R plus or many natural numbers. And no, okay, this would be your integers because you can take negative values, and this would be natural numbers, something like that. So one example of policy could be mu k xk is equal to xk minus xk if xk is less than sk otherwise. So these are known as threshold type of policies. So this xk you need to find out. That is the whole problem. You need to find out the thresholds at each time point, and you'll see that what happens is at suppose time 1 you have S1 threshold, and then you see where your X1 is, and you say that, okay, my S1, and then middle you have your X1 goes down, and then here you compare, and then you order, and then you again go down, and then you again order. Your S1s, S2, S3, they could have different threshold at different timelines based on how much low or how much high you are from threshold. You order or you don't order. So suppose your threshold is here, S3, you don't reach there, you're above S3, you keep on, and your S4 threshold is here, then again you order. So this is one type of policy that you can come up with, where you come up with these SKs, this is basically a parameterize your optimal function. These are known as threshold policies, and we'll see in the later classes that they play a role in optimal things. But yeah, for today, I'll stop here. But yeah, so
So can you explain, open loop and the closed loop thing?
yeah, sure, sure. So, in the open loop problem, yeah, this open loop problem. So what happens is, okay, I'll do it in the inventory control setup. In the open loop problem, oh, maybe I can. Yeah, in the open loop problem, okay, so this is your inventory system. You give your input xk, you give your input uk, okay? You get some wk disturbance from the outside, and then you produce xk plus 1, right? Take this xk, take this uk, you have this cost function that you're trying to minimize, right? Now, how do you take these decisions? Do you take this decision? So if you have this link of no, before taking UK, you give this xk to that UK, and based on this decision, you take what UK is and then give it to the. If you have this connection, then it is a closed loop system. If you don't have this connection, if you directly, without knowing what xk's are, you directly give UK to the inventory system, then that is an open loop system. So here, this policy that I have written down, since UK is a function of xk, at each time instance, you know what xk is, and then you will get what UK is.
Okay, okay,
Then it's a closed loop. So basically, closed loop means you have a system, you have your state xk, you have your output, mm, that will be your xk plus 1, and now you give this back as a control. Now this back feedback that you're giving back as a control, as a function of xk plus 1, this is your control. This is what is telling you that this is what is closed loop. If you don't have this feedback, you don't know what the states are. Then you're blind. You're saying, okay, first I do U2. I don't know what my state is. Then I do U1. I don't know what my state is. I do U3. I don't know what my state is. That is open loop. Open loop basically always you'll not do good in open loop because you don't have that feedback and you don't know where the state is going. It's better to have feedback always. So we'll always look in closed loop scenarios, no open loop. But there are uh, what do you say? Two types of methodology like you can solve. Is it clear?
yes, yes, yeah. Thanks.
Um, any more doubts? I'll stop the recording.